So our first presenter for the day would be Marie-Louise Kloubert, that will present us the paper titled Assessment of Generation Adequacy by Modeling a Joint Probability Distribution Model. Marie-Louise has indicated that she would like to make a live presentation. To introduce our speaker, Marie-Louise received a PhD in 2009 in probabilistic modeling for grid planning from the Technical University of Dortmund in Germany. She has been working since 2018 in the system operation at Transnet PW, which is the German TSO, focusing on the task of generation adequacy modeling, development of data concepts, and data use. Marie-Louise, if you are ready, please open your microphone, share your screen, and we are very interested in your presentation.
Hello, everybody. Can you see my screen already?
Yes, thank you. This is working very well.
Okay, then thanks a lot for the introduction and welcome to my presentation to the topic Assessment of Generation Adequacy by Modeling a Joint Probability Distribution Model. First of all, some words for the problem statement. So as you all know, energy generation and energy demand need to be balanced always. And the energy generation consists of the generation by renewable energies, conventional power plants and storages, and the import. And on the other hand, the energy demand consists of the national demand and the export. And considering the energy transition, the question arises, is there always sufficient generation to cover the load even during peak load? And if you have a look at the future, then there's a high amount of uncertainties, and the uncertainties grow over the time. So on the one hand, if we start here with the load, then it's unclear and unsure how many electric vehicles will be there. How about demand side management, heat pumps, e-trucks? Will there be new technologies, and how is the overall load? Will it be growing or will it be reduced? Then on the other hand, storages are coming into the grid. How many PV storages will be in the future? Storage batteries, power to X, and pump storages. And on the other hand, the generation park, it's unsure how many power plants will be based on oil, coal, nuclear, gas, and so on. And on the other hand, how many renewables will be in the grid. And these uncertainties depend on political, social, and economic developments, but also depend on individual behavior. So if you want to have a look at the generation adequacy for the future, we need a fast and flexible method to analyze a lot of different scenarios. So I'm proposing to develop a multivariate distribution function to model the dependence between uncertain input variables. And if you have a look at the figure, it's the figure shown for two uncertain variables. That's how a multivariate distribution function would look like. In my example, I will have more than 180 uncertain variables, and it gets high dimensional, and we cannot figure it like that anymore, but just to get an image of it. So the function is based on a COPULA approach, and the idea is to model the marginal distribution function and the dependencies separately. And I will show you how it is done if we have a small problem with 4 uncertain variables, and I'm using a pair COPULA approach. So if we have 4 uncertain variables, you can see these trees I'm building up. And the first tree is calculated, then the second tree and the third tree. And if you have these 4 uncertain variables, you can see at the end of the slide, you can see how you will calculate these multivariate distribution functions to model the dependencies between the variables. So in my case, there are some important uncertain variables considering the generation adequacy. And the generation adequacy depend on wind speeds, solar irradiation, load, and the unavailability of conventional power plants. And on the right side, you can see Germany and 91 stations. They are throughout Germany, and these are weather stations by the DWD, the German weather forecast. And at these 91 stations, I analyzed the wind speed data taken from the DWD for 20 years. And at the same station, I also have 91 stations for solar irradiation, then the overall load for Germany, and the unavailabilities of conventional power plants taken by the publications on the EEX. And following the approach, I'm first calculating the marginal distribution, and then in the second step, the dependence structure. So here you can see the box plots for all 91 stations throughout Germany. And as you may know, there are some difference between the wind speeds for Germany. So in the north, we have some high wind speed, and also on the mountains, of course, there's higher wind speed, and in the south, there's less wind speed. So there are some difference if you're having a look at the box plots. And for all stations, now I checked which density function fits best. And for all 91 stations, I could find a Weibull distribution function to fit the distribution. And here in the picture, you can see the distribution function at station 49. And 49 is in the north of Germany, so there's quite a high amount of wind speed. So I've done the same for the solar irradiation. It's again, I've checked first of all the box plots, and comparing to the wind speeds, there's not such a big difference between the box plots for all 91 stations, but still, if you have a closer look, then you can still see some difference between the stations. So then again, I checked which density function fits best to model the data. And as an example, I show here the station 43. It's in the middle of Germany, and I fitted it by the non-parametric kernel estimate. Then in the next step, I checked the load. I just had the data for whole Germany, so it's one load time series for whole Germany. And as you can see, it's a B-model distribution function consisting of two modes, and it's because of the weekdays and weekends, so there's different kind of load demand. And then in the last step, I checked the distribution function for unavailabilities of conventional power plants. It looks a little bit like a Weibull distribution, but again, I fitted it with a non-parametric kernel distribution estimator. Then in the next step, I need to calculate all the dependence structures as shown before in the trees. And so I calculated the dependent structures for all trees, and here you can see the overview of the selected families. And yes, there's a high amount of T, COPULA, and Frank and Clayton, but there's also some others, and the rotated COPULAs show a negative dependence. And as you remember, I wanted to calculate such a function as we see in the figure right. Here's some exemplary results by the C-Wine COPULA model. So, for example, I checked for 90% of all stations. I wanted to know in how many cases the wind speed is higher than 10 meters per second for 90% of all stations, and at the same time, the load should be smaller than 55 GV, which is quite small for the German load. And the modeled probability is 0.006, 0.03%, and the empirical probability is 0. So it wasn't monitored in the past, but still it could be possible. Then maybe I can go to the last line. So in how's the probability that at 90% of all stations, the solar irradiation is smaller than 100 watt per square meter? Then the model says it's 58%, and the empirical data it's 57.5%. So it's rather the same. And so I followed the model works well, and now I'm using it for the generation adequacy analysis. So now I want to have a look at 2030, and you can see the scenario data for the installed capacity. It's taken from the TSOs, the data they use for the network development plan. And first of all, I calculated the residual load and the probability that the residual load is greater than 0, for example. It's 62%. And yeah, for generation adequacy, it's interesting to check the residual load greater than 50, 55, or 57.5. So for 50, it's, for example, 0.8%. And now I'm checking the remaining capacity. And you can see that the remaining capacity is normally positive. Just in a few cases, we can see that they are negative remaining capacity. You can see it's zoomed out on the right figure. So in this scenario, the generation adequacy problem is rather small. Now I checked for another scenario because, yeah, as I told you before, it's quite uncertain how the scenario will look like in a future scenario. So I reduced the thermal conventional power plant from 61.1 to 55.1, and the others kept the same. And the negative remaining capacity grows in these cases. And yeah, that's but it's just checked for Germany. So in the next step, the model will be extended for Europe to consider the possibility of import and export. In the case before, of course, it's still possible that we can import energy from the other countries if they have sufficient energy. Then in the next step, storages and new loads could be integrated, new loads like electric vehicles. And then I just showed it for 2 scenarios, but of course, 2 scenarios are still not sufficient to analyze the generation adequacy for 2030. So the idea would be to make several generation parks and load developments to show the range of possibilities for the future. And in addition, the model could be extended to evaluate transmission adequacy. Then thanks a lot, and I'm happy to answer your questions.
Thank you, Marie-Louise, for this very interesting presentation. Maybe I can ask a first question before the session attendees start using the Q&A facility. So one of the things that you mentioned both in the introduction and here is the potential to integrate the storage in this model. I'm wondering how you are thinking to manage the time coupling in the storage devices, because if I understand correctly, right now you don't have a time dimension in your model.
Yeah, that's true. I also want to do it with historical data. Of course, it's a little bit problematic because it's a question if the historical data is representative for the future scenario. But there are data available for the pump storages and the amount of water, for example, in the pump storages. So I would like to check this, and maybe it's good to do some sensitives to model it with historical data, but also to take some other assumptions and then to check how the generation adequacy will change.
Okay, we have one more question, which was asked privately. The question is coming from Simon Tindemans. So the COPULA model finds the best fit for dependent resources on average. Generational adequacy is about behavior at the extremes. Do you think the COPULA model trained on typical behavior works well for the extremes?
Yes, it should calculate the overall behavior and should also include the extreme behavior. So there's I don't know why it shouldn't integrate the extreme behavior.
Okay, Simon, since you are also a panelist, you may unmute your microphone if you wish to react to the comment.
Thanks. Yes, here I am. Yeah, so thanks. No, it could be, indeed, it does model, I think, extremes as well, but I just wonder, for example, there's some evidence, I think, from kind of historical data in the UK, for example, that the kind of codependence between at least load and wind, for example, is not exactly, during extreme cold spells, may not be exactly the same as it is typically. So you might need a kind of like a different copula, maybe a different fit for the extreme values than for all data.
But you can see the in the historical data from UK, you can see the historical data for the load, for high load, and for wind speeds.
And then winds. Yeah, so I refer to a study, it wasn't by me, so it was Chris Dent and Amy Wilson and Stan Zachary, so I could send it to you privately. I think it's
yeah, that would be interesting. Yeah. So I can check it. But I think if it's seen the historical data, I think the model will also include this, also extreme values. But I would be interested in to see the paper you're talking about.
Okay, thanks.
Okay, it seems like we have reached the point where you, let's say, are more interested to follow up on this after the session. So let us all thank Marie-Louise for her very nice presentation and move on with our next speaker.